Okay, I think it's time to start. Hello. Okay, yeah. Any question from last time? We were having quite a few break. Last time have you watched the it's a video from last year. Hopefully people are okay with it. Okay, and yeah. Then let's get away from ISA and let's get back to content. So more about global algorithm. We basically, maybe talk about organization first. So I think we basically finished everything that we need to talk about. So today I will finish something about Grover. So maybe I will talk about these distinguishing states. That's like a bit of a loose end on Grover's algorithm, and then we'll maybe talk about some applications. There are a lot of applications here, but maybe we'll pick an easy one to talk about. Okay. And yeah, and there is classification about different parameters you can choose for Grover's algorithm. And so anyway, today will be the last class that we teach material. And I think on Thursday, let's just have probably one class of final review. And then next week will be final week, so final will be on Thursday. So I think we just take another break from next Tuesday and let you have a final on Thursday. Okay? Okay. Yeah. Okay. Then let's go back to Grover's algorithm. Okay. So a bit of a review. We are proving optimality of Grover's algorithm. Okay. So this lower bound is actually not really a lower bound for Grover's algorithm. It's a lower bound for the search problem. So it's asking, so given this truth table, your function is this function O0 or is there 1 somewhere? Okay. And we want to do this query complexity lower bound. So we ask that we think our query algorithm look like this, although it's a bit simplified. So I think we input as 0 and we do this unitary and oracle, etc. And we ask how many of these. So unitary are free, but we're asking how many of those oracle you need to apply for your final state to distinguish in these two cases. So you want to distinguish yes case and no case. So yes case, so it's a bit reversed, but yes case in our definition here is you think this f, small f, which is actually an input, is all 0. Okay, so there is a small f and a big F. Small f is basically the input to this problem. So this decide what this OF will tell you. And there is a big F that's a function of this small f, and it's this yes/no question here. So this big F here is a decision version of search, which asks whether this small f is all 0 or is a 1 somewhere. Okay, and then we ask how many of those O of small f do you need to put in your algorithm for your algorithm to solve this decision problem. So anytime your small f is 0 input, you should get some 0 input state. And if there's some 1 input, then you should get some 1 input state as an output there. And then we lower bound this by showing that, well, by basically defining a progress function. So we ask how much difference so we think about the state evolves through this algorithm, and then we think about how using different small f will change this evolution. So we kind of think of this evolution as some kind of trajectory, and at the start of algorithm, no matter what your small f is, your algorithm should start with the same quantum state because it starts with the same 0. And this U0 doesn't depend on small f, so it will just turn everything to the same psi f0. Okay? And so only those OF will change the pace of, only this O of small f depends on small f, so this is the only part where you can distinguish between a yes and no case. And we say at the end, you need to have good probability to make a decision on this yes and no. So at the end, the small f in yes case and small f in no case should give you pretty different quantum state here. So you start with the same state and then you start with different state. And we also say in the middle, all the small f doesn't change the state too much, and so that's how we can bound it. And to make the distance thing more concrete, we define this distance measure as sum over sum over some pairs of f and f prime, where f is those small f in the yes case, and the f prime is the small f in no case. So there is some relationship you need to choose here. Okay. So some f and f prime in some R, I guess, in R, in some relationship. Okay. And for example, the relationship look like this for our search problem. Okay. So anyway, we sum over some pairs of those the distance between psi f and psi f prime, and sometimes with t. Okay. So yeah, so this is our progress measure, and as we said, this progress measure is 0 when t equals 0, because every quantum stays the same. And at the end, we argue that it must be some constant times the number of pairs you are summing over. Okay. And then we go into more detail. So now we need to pick our relationship for our search problem, decision version of search. So these small efforts, so this yes case, there is no choice here. There is only one one instance that give you yes, that is all zero input. And for no case, we choose those 1 0 0 0 0 1 0 0. So there is only one mark item. Things like one mark item and no mark item, things pretty hard to distinguish, right? And so we pair them all together, and we calculate the distance. Okay. So that is distance. So this psi k is quantum state for all zero input, and psi xk is the quantum state with mark item, only one mark item on the x location. Okay. And so we calculate this distance, and then okay, and we give inductive proof, and saying that induction proof is showing that this distance cannot grow too fast, so it grows quadratically with the number of query use. Okay. Okay. And so the proof we do some hybrid between these OX and psi k, etc. And and Cauchy shows, etc. And we are able to complete the induction. Okay. And in the end, at the end we need to show this kind of a state distribution problem. So we are saying for the yes instance, there is a projector that accepts yes instance with low probability, and for a no instance, there is a projector that accepts it with high probability. It's kind of reversed, but it's okay. Yeah. So we're saying at the end you want to do a two outcome measurement, and without also generality as a swing projector. So there's a projector, and it's a complement. That's a final measurement you do on your algorithm, and somehow we have it reversed here. We say yes instance we want low success probability, and no instance high success probability. So P is more like rejection. But anyway, yeah. And so if we have this, then we prove that the actual thing we want is we want psi t and psi tx is a constant distance for every x. And for that we show a bound. Okay, so we want those two vectors to be pretty far away, and what we show is the linear product is pretty large. Okay. And we're able to, from those two numbers, and show that their inner product is at least, we want to say the inner product is small, because we want the vector to be far away, so inner product needs to be small. Okay, so the inner product is most 2/3, and that means this distance measure is most 2/3 too. Okay, and so that completes our lower bound for the search problem. Okay, any question? The search problem, but actually a decision problem. Problem so far. Wait, why am I'm confusing myself. Oh, okay. D is okay. Yeah, D is actually the distance different squares summing together. Okay. Okay. No question so far. Then let's go into a little more detail about bounding and final distance. Okay. So this bound is beyond tight, although it suffices for our proof because you only want to bound to some constant vector, and you can always amplify your final success probability to any constant. You can just repeat your algorithm a few more times and do a majority voting, then you will get a smaller constant here. Okay, and yeah, so you can always get this small constant and bound the distance. But now we go into a bit of information theory. Okay, so now we will just want to say on the final part of this lower bound, can we do a little better? And so if this 1i, n(i) is this is this 2/3, or this 2/3 the best we can do, and it's actually not. Okay, so we are going to show 3 tight bound on this thing. Well, so let's do a little calculation. So assume this number, so if it's epsilon and this is 1 minus epsilon, okay? So if this number, let's use probably yellow, okay? So let's say the epsilon, then we will have this number is square root epsilon. And what we get is we show the inner product is less or equal to 2 square root epsilon. Okay? And then we claim that this is a beyond tight because what you can actually get is 2 square root epsilon times 1 minus epsilon. So you get extra 1 minus epsilon factor here. That's a tight bound. Okay? And yeah, so no objection, then let's go to better bound. Okay. So now it's more about information theory because for the purpose of Grover lower bound, this is enough. But now we want to do a bit of quantum information to see how the distinguishing probability and the inner product between 2 vectors are related. Okay. Okay. So what's our lemma? So as we said, we suppose we have a 2 quantum state and we kind of want to distinguish them. And so there is a projective measurement with a measurement operator P and 1 minus P. So there are 2 projectors, or more like I minus P. Anyway, so you have these 2 outcome projective measurement, and they distinguish A and B pretty well. So so we find out that A got associated by P is less than square root epsilon, and so that means P 1 minus P. So maybe that's also the right thing, because the probability on P and the probability on 1 minus P should sum square to 1. So this also means 1 minus P on A square root is greater than 1 minus epsilon. And okay, so A got accepted less than epsilon, but B got accepted greater than 1 minus epsilon. Okay, so they distinguish A and B pretty well. Okay, so this also means 1 minus P on B is less than epsilon. Okay, so when you have, so you do this 2 outcome measurement and you input A and B. And so A has a pretty good probability to get this 1 minus P outcome, and B has a pretty good probability to get this P outcome. Okay, because they are greater than 1 minus epsilon, and we think epsilon is kind of a small number. Okay, although at the end our epsilon should be between 0 and 1/2, so it can be not so small. Okay, and we claim that if you have this kind of distinguishment, then A and B inner product will be less or equal to 2 square root epsilon epsilon times 1 minus epsilon. And this is pretty good because even when epsilon is close to 1/2, yeah. So even when epsilon, so example, let's see, epsilon equal to 1/2, then this equal to 1. Okay. So the worst one is 1. Whereas before we have if epsilon is greater than square root 2, then this bound will be more than 1, but that's impossible because the largest of the inner product is 1 only. Okay, and yeah, so this is more tight. Okay. Anyway, let's go back to the bound. Okay, so first prove how do we bound this better. How we bound better? Basically we do the same thing. So remember here, what we do is we have an inner product, then we insert P and 1 minus P pair inside. So we split 1 into 1 minus P and P. And then we split this into two things. And we basically do the same thing here. But, so we also split to P and 1 minus P, but then we use the fact that the P and 1 minus P are projectors. So P equal to P squared and 1 minus P equal to 1 minus P squared. Okay? And so this just gives us better bound. Okay? And now this norm of APPB is we can think as these are the inner product of AP and between and the inner product of PB. Okay? So you have a norm of P on A and a norm of P on B, because the norm of bra is the same as the norm of Kate. And similarly here you have norm of 1 minus P on B and 1 minus P on A. And we change the order a little bit here because we know what we are going to do next step. And what we are going to do next step is we are going to do Cauchy-Schwarz inequality. Okay. So Cauchy-Schwarz inequality says that for two elements, x1, x2 plus y1, y2 is less or equal to square root x1 squared plus y1 squared times square root x2 squared, y2 squared. So we are thinking of this as the inner product between the vector x1, y1 and x2, y2. Okay? So inner product is less than the norm of two vectors. Okay? And now if we just use this formula, then x1 is here and the y1 is here. Okay? And x2 is here and the y2 is here. Okay? So we have a square root of p of a squared plus is 1 minus pb squared, and then here we have a pb squared and 1 minus pa squared. Okay. And so why we want to do this? Because now these two terms have a nice relationship. Because if we look up here, so we compare those terms. So why we want to do this? Because those two terms. So if you look up, then the PS squared this is like a less than epsilon term, and this is also less than epsilon term, and this is a bigger than epsilon minus 1 term. Oh, sorry, this one is this. So this is bigger than 1 minus epsilon term, and this is also bigger than 1 minus epsilon term. Okay, and yeah, so we'll feel that this should be like a 2 epsilon, and it should be 2 1 minus epsilon. Okay, and indeed that's just finish that intuition. So, but they are not exactly epsilon, so we need to be a little more careful. So if those are all equal sign, then we're already done, right? If they are all equal sign, then this part will be about 2 epsilon, and this part will be about square root 2 epsilon, and this part is square root 2 1 minus epsilon, and we are done. But they are less or equal, so we need to do a little more. So they are less or equal, so let's say this two sum is x, and then by the relationship up here, this two sum will be 2 minus x. Okay, because this plus this equal to 1 and this plus this equal to 1. So their sum, so sum of those four terms should become 2. So if this x is 2 minus x, so we have the inner product here is square root of x and 2 minus x. Okay, and yeah, then we just need to show that, say that this thing is monotone. Okay. Okay. And So we know our x is then, we know our x is less or equal to 2 epsilon because, because this is epsilon less than epsilon and this is less than epsilon, so this is less than 2 epsilon. Okay. X is less than 2 epsilon, and how does this function look like? Is a square root of this inverted hyperbolic equation. Okay. And so if you plot this, and so this function starts with 0 when x equals 0, and go to 0 again at x equals 2, and then it is peak at x equals 1. And anyway, anything you want to know is that, actually we plot the x as 2 minus epsilon instead of square root, but square root doesn't change the monotone. And anyway, so we see that if you try to plot this function, so we see it's increasing between 0 and 1. Okay. It's increasing between 0 and 1, and we say epsilon is less than 1/2, so that's just, I guess I can equal to epsilon less than or equal to 1/2. So this 2 epsilon is on this side. So if x is less than or equal to 2 epsilon is on the increasing side, then this will be smaller than just putting epsilon as x. Okay, and just putting 2 epsilon as x. Okay. Yeah. And so we can get our 2 epsilon here as a bound, and we get our inner product bounded by 2 times square root of epsilon times 1 minus epsilon. Okay. Question. And okay. So that's our proof. We are writing this once again. I guess I should not write the if here because that should be given. Because we want the distinguishing to be, the worst possible distinguishing you should get is epsilon equal to 1/2. Right, so it's like a 50-50 probability to get each. And so if epsilon is greater than 1/2, then you should just swap p and 1 minus p. So these two will swap. Okay. So that's the first proof. We just need to do this separating into 2 parts more carefully. Okay. It's very algebraic. Any question? If not, then let's talk about the next proof. So next proof gives us more intuition. So we are drawing geometry about our distinguishing between our vector A and B. But it's not quite a proof, it's just because it's not rigorous, but we are just showing how this looks like geometrically. So how do we distinguish those two things A and B? Okay? So let's consider we have 2 vectors, and let's consider 2-dimensional plane layout. And so other dimensions are really not very important, so let's just assume we're on this 2-dimensional plane. And on this 2-dimensional plane, how do we distinguish A and B? What we do is we place A and B in like this symmetric axis against the 45-degree line, and we do a 0-1 measurement. Okay, so we do the 0 measurement as P, and the projection on 0 as P, and the projection on 1 as 1 minus P. Okay, so what happens is, and so we think if B and 0 has some angle delta here, and A and 1 minus 1 also have some delta here. Okay, so why not just write this delta here too? Okay, so we have a delta here and a delta here. Okay, and we kind of just claim that this is the best way to distinguish between A and B. Okay, when you want to minimize the largest possible error. I think it's kind of intuitive. Okay. Because okay, and so I think B is B closer to 0, so when you measure, you do this 0, 1 measurement, and so if you input B, you are more likely to get 0, and you input A, you are more likely to get 1. Okay, so what is the error probability here? So the error probability is you input B but you get 1, or you input A and you get 0. And probability here is the projection of B on 1, so that's the sine square of this delta here. Okay, and yeah, so the error is sine square delta, and as it says, is error probability should be less than epsilon or about epsilon. Okay, so error is this thing, and then what's the inner product? Inner product now we can read geometrically. So we know this delta here, and so the angle between A and B is actually pi over 2 minus 2 delta. Okay, and so the inner product here is this cosine pi over 2 minus delta, and now we just need to do geometry. So cosine pi over 2 minus 2 delta, then that's sine 2 delta. Okay, and sine 2 delta, I just use this formula is 2 sine delta cosine delta. Okay, and yeah, but we say sine delta is, well, sine square delta is epsilon, so sine delta is about epsilon, and then so sine square delta is about epsilon, then we also have cosine square delta is 1 minus epsilon. Okay, and yeah, so you combine these two, although it's bigger and less equal to, but I think if you are doing either being more careful, then you can do the same thing and get the upper bound. But here we are lazy, so we just say sine delta is about epsilon, and cosine delta is about 1 minus epsilon, is about square root 1 minus epsilon, so this whole thing is 2 square root epsilon times 1 minus epsilon. Okay, so yeah, so this gives you a bit more intuition, so you can, but obviously this is not quite a proof. Okay, because there might be other way around. Okay, but this gives you an intuition about what's the best possible measurement you can do to distinguish those things. And you can feel that if you do this measurement, then if delta gets smaller, means A and B are getting closer to 0 and 1, and they will have larger angle, and that's why the inner product gets smaller. Okay. And okay, so this is proof number 2. And proof number 3 is the easiest possible proof, but you cannot quite do. But so proof 3, you will use a better concept. Okay, so this is a concept that's in chapter 9 of the book. But it's actually quite fun, although we don't have time to cover here right now. Hopefully this gives you some motivation to read chapter 9 yourself. Okay, so they introduce those I guess information theoretical quantity. Okay, so if you want to study, so on a very high level, what we want to do here? What we want to do here is we have 2 state A and B, and we want to study their distance. Okay, and to study the distance between 2 quantum states, yeah. So I should say, like, to study the distance between 2 quantum states, people found out that there are 2 quantities that are very useful. The first one is trace distance, and the second one is fidelity. Okay, and but you might ask that actually, if we have like 2 quantum states like A and B here, then it's pretty easy to characterize their distance. So you just take inner product, and yeah, inner product will just tell you what's like so if you know inner product, then basically you know the geometry between those 2 quantum states. Then why do we have these 2 distance? So we have those 2 distance because we are using a machinery that's like too powerful for what we want to do here. So those 2 trace distance and fidelity are defined for the distance between mixed state. Okay, so if you want to study distance between mixed state, then the cases are more complicated, and so it makes more sense to distinguish between trace distance and fidelity. transience fidelity are used for mixed state. Okay, so they are used to quantify the distance between mixed state. But here we are doing a very toy example of transience and fidelity because A and B are pure state. Okay, and anyway, so to give you some idea, some intuition of transience and fidelity. So what's the intuition of transience? So the intuition of transience is exactly one of the property we have. So transience is the upper bound on how good you can distinguish two quantum states. This is even for mixed state. Now we all use it only for pure state. Okay? So transience is the upper bound between the bias between measurement probability you can get on those two things. And so what's the bias? So we were saying that when we do this, remember we say that when we do this P and 1 minus P measurement and say the probability gap associated by P is 1 of them is epsilon, 1 of them is 1 minus epsilon. So gap is just the difference between this 1 minus epsilon and epsilon. And so it's 1 minus 2 epsilon. Okay? And so here we also have some formula for transience if you actually have the mixed state. Okay? But operationally, transience just quantify. Operationally, transience quantify how well you can distinguish two quantum states by some measurement. Okay? And then what's fidelity? Well, fidelity actually is just inner product. Well, for pure state, it's inner product. And for mixed state, there is a weird theory about. Okay, so for the mixed state, it's actually like you take a two density matrix and it's largest inner product when you purify those two matrices. Okay, it's a bit more complicated. For now, we just remember that for pure state, fidelity is the inner product between them. Okay. And for mixed state, there is some weird way you can define inner product between mixed state. Okay, and okay, so that's transience and fidelity. So from the two things we have, we see that we want to calculate fidelity we want to bound fidelity from transience. Okay, so how do we do that? Is actually for pure state, it's very easy. Pure state, we just have this relationship: fidelity squared plus transience squared equal to 1. Okay. And so then we just go through things. So what we want is the fidelity, and from factor 3, it's just square root of 1 minus transience squared. And but now we have I think we have the lower bound on the okay. We have lower bound on transience, I think. So that will be upper bound on this thing. Okay. So we see the transience is about we have a lower bound on transience. This is 1 minus 2 epsilon. And so it will turn into upper bound on this square root of 1 minus t squared. So it's an upper bound on 1 minus 2 epsilon squared. And so we do the calculation here, so just expand everything out, then we get back to this 2 square root of epsilon on 1 minus epsilon. Okay. Okay. So that's a bit of information theory. Okay. And so these two factors are only when the states are pure. And when you have a mixed state, then you need a more complicated thing. Okay. Okay. Any questions so far? If not, then we have finished 15 minutes to talk about random thing about global algorithm. I guess the first thing we want to say, okay, so it's really long here, but I guess I can say it really short. Okay. Maybe I should not say all global algorithm. Okay, so we have been talking about the decision version of search problem. Okay, and So instead of talking about decision version of search problem, sometimes people call it OR function. And why is that? It's because if you think about the input not a small f, you think about the input as just this truth table of small f as a string. And what we are trying to distinguishing is whether this string are all 0 or string has some 1 here. Okay? And you can do that by just compute the OR function of all those bits, right? So if they are all 0, then you compute the OR function, then it's 0. And if there is a 1, you compute the OR function, then it's 1. Okay? So yeah, so that's really quick. So if you think about talking about a function on this truth table, then we can say this decision version of search is just computing the OR function of the truth table. And then very theoretically, we can say this quantum query complexity of OR function is a big theta of square root n, because we have an upper bound by using Gover algorithm. Gover algorithm will solve this in square root n time. And lower bound, and we just prove it. Okay. Okay. And okay. And that is that. And but here the upper bound is a little weird, right? Upper bound we say. I guess here we are using for unknown m, so it's okay. Okay. Yeah. And then one thing we want to jump here is we want to talk about, well, not really modification, but we want to talk about basically different specification of Gover's algorithm. Okay? So we have been saying that Gover algorithm using square root n over n times step. If you have a total n item and there are n mark item. Okay? But okay. But we are saying that now we have a small problem on this m here, right? Because we need to know the number of m here. Otherwise, if we keep running a Gover algorithm, we'll overshoot. Okay, and so there are different things you can ask on this algorithm. Okay, so it's whether the m is known to you or not known to you, and can you turn the error probability of algorithm to 0? And it turns out that this is a quite interesting problem because you can put this table. So for and we have a different result here. So if you only want constant error, then you can not knowing m. And if you know m, you can turn error to 0, but you cannot get both. Okay, so the weirdest one is here. So if your m is unknown and you want 0 error, then it's actually impossible to get Gover speed up. It's omega n over m. Okay, and as we say, so original Gover we introduced in class is this result of the square root n over m. And then when m is unknown and error is constant, we argue that we can still do order square root n over m. And that's by either the quantum counting or binary search. Okay, although the quantum counting is also a little weird. Yeah, but we argue that we can do some binary search on m, and you can still get so you only lose a big constant factor here, and you can still get constant error with the square root n over m. Okay, and 0 error we can that. If you know m exactly, then you can actually rotate this precisely. So you can basically make your rotation angle a little smaller and make this probability precisely 1 when you reach around here. Okay, so you only use square root n over m, and it's at the end of this slide, so you can look up yourself. I think this is on the website. Okay. And then number 4 is something we'll not talk about. Okay, so you can actually give a lower bound on these things, so you have no error and number of m is unknown. And it's a lower bound by a different method that we'll not talk here. It's a really interesting method. It's called polynomial method. So basically, you show that you show that the success probability of your algorithm is some polynomial, and success probability of your algorithm is some polynomial, and something very weird happen is the degree of the polynomial is related to the number of query. Okay, and and so you can show that. So this is a general result. The success probability of algorithm is is a polynomial where its degree is basically linear to number of query you put inside. And then you just show that your problem need a larger degree polynomial to have the success probability you want. And so the larger degree in a polynomial translate to larger number of query here. But it's a subject that we don't have time to go to detail. Okay. Any question? Okay. If not, then let's also talk a little more about the jump. Okay. And there's 10 minutes. Let's talk about some, I guess, a bit more theoretical application of global algorithm. So here we have an application of global algorithm that's like you can speed up a complete problem a little bit, but there are some tricky points because sometimes the square root speed up is slower than classical algorithm using dynamic programming. But what I want to talk about is kind of this. So actually you can, theoretically what people like to do is doing this nested global search. Okay? So we say global search is like solving for the OR problem. And so if you have OR, then what if you want to solve end of OR? Okay? So think about there's a weird problem. Okay? So now it's a bit tricky. So now we always think of input as a truth table. So this square block here is a truth table of some small f here, and we just put it in this square because this is more nature of what we want to compute. Okay, so we have this bigger input number, and we list them in this square root n times square root n block here. Okay, and so what we want to calculate is the order of n on this block. And what does this mean is we want to calculate the end of every row first. So here we have the end here. And and so this row has 0, so it's 0. And this row contains 0, so the end is 0. And only this row has all 1, so it's 1 here. Okay? So we want to compute the end of first row here, every row here, and you compute the order of everything here. Okay? It's a kind of a weird function. You compute and order of end of this block. Okay, and so what does this function do is asking, does this block contain a row that has all ones? Okay. So for example, this is a ENS instance because you have a row that's all one here. And you will give a 1 here, so when you order through all those numbers here is 1. Okay? So order of all those end of rows. Okay. And okay, so when we talk about this question, then now we're back to query complexity. So we ask, so your input have this thing, and you want to calculate order of end of it. Then how many query do you need to compute it? Okay. And so classically, it's easy to see that you will need omega n queries. And quantally, then we show that, okay, so let's jump through, jump away from the beta thing. Okay. Do we have time? 5 minutes probably. Okay. Guess 5 minutes we have enough time. So quantally, then you can use global search to speed this up. Okay, and so if you do this in dump way, so you say you can for each row you can do a global search. So there are square root n item, and you want to calculate end of them, but calculate end of them is basically same as calculate all of them. Use that kind of negate everything and calculate all, okay? And then negate back, okay? So you can calculate the end of each row by go over the algorithm and take a square root and query, okay? And square root of square root n, so that's n to a 1/4, okay? And then if you just do classical, then you just so each one take n to a 1/4, and so you calculate this, then you just do classical post processing, then then the total number 10 you need is there are square root n rows and there are square root n rows and there are each row take n to a 1/4, and okay. And also there is HR log n factor because you want each row to have small error, so you don't want to just constant error on this thing. You want those error on those numbers to be 1/n, so you get the HR square root n factor. Okay, and yeah, so total number of times is n to square root n times n to a 1/4 times log n, and then there is the HR square root n classical post processing of you can just go over the result you calculate here. Okay, and so that's a slower one, but what we want to say is actually it's possible to run your go over algorithm recursively. So we say we can run go over algorithm to calculate this result here, and but this go over algorithm is a quantum algorithm. So we can think this go over algorithm of calculating this thing and get this result as a kind of an oracle that you can feed to another go over algorithm. Okay, so when you think it this way, then you have this recursive go over algorithm. Okay, and so the inner go over algorithm, as we say, will run about square root of square root and 10. That's how much time you need to calculate one of this output. Okay, and now this inner algorithm run as oracle, and then outer algorithm, you are go over this square root and square. You are once again doing go over algorithm over this square root and number of items. So total number of times is outer go over algorithm need to run square root n over square root of square root n queries, and where each query is answered by the inner go over. So each query needs this many times. Okay? So you total need the square root of square root n times square root of square root of 10, and then once again need some log n factor because you want the inner go over to have low error. Okay. And yeah, so total number of query you need is just square root n times log n. Okay. Yeah. So this is a concept that is very useful. That is, you can run go over algorithm recursively. Or in general, you can run a lot of quantum algorithm recursively. So you can think about you have a quantum algorithm solve a subtype of a problem, and you think that as an oracle that you can. This sub-algorithm, you can treat it as an oracle that feeds into a larger algorithm, and so you can run this thing recursively, and you will get a better time and space, time and query complexity. Okay, and yeah, so we see that for this order of n problem, if you run this recursive scheme of global algorithm, then once again you get this quadratic speed up over the classical algorithm. Because classical algorithm you need omega n queries, and it's easy to show that this is also optimal. Okay, yeah. So the idea is you treat the global algorithm that compute the end of some row as an oracle. You can turn the quantum algorithm as an oracle to another quantum algorithm. Okay. Okay. And I think it's just about time. So that finish anything you want to teach in this semester. So so as we say, we'll have midterm review on Thursday. Sorry, not midterm, final review on Thursday, and yeah, hopefully, and then we'll do final on next Thursday. Okay. So see you on Thursday.